Sorry, I'm not sure what happened there, so let's start the proof again. So by definition, the numbers r, lambda, mu are integers. And let's let h mu be one of the terms in determinant of h lambda. And let's say lambda equals lambda 1 through lambda L. So this is a determinant of an L by L matrix. Now we want to show that mu has to be greater than or equal to lambda in dominance. And if it's equal to lambda, then we're going to get a coefficient of 1. So if h mu is one of the terms in the determinant, then h mu equals h mu 1, h mu 2, up to h mu L. And let me write this as h beta 1, h beta 2, up to h beta L, where this is the contribution from the first row, and this is the contribution from the second row, and this is the contribution from row L. Now we don't necessarily have beta 1 equal to mu 1. These are a permutation of that because we didn't necessarily get the greatest index from the first row, the second greatest index from the second row, the third greatest index from the third row, etc. So beta 1 through beta L is a composition of L. Sorry, it's a composition of N, where lambda and mu are partitions of N. It's a composition of N that has L parts. Now if h mu comes up in the W term of determinant of h lambda, so the determinant is the sum over all permutations in SL. H lambda, the 1W1 entry, H lambda, the 2W2 entry, etc., up to the LWL entry. Then beta k is going to be lambda k minus k plus wk for each k. Now let's look at the partial sum mu1 summed up to mu k of mu. So hopefully for any k, this is greater than or equal to lambda 1 summed up to lambda k. So first of all, mu1 summed up to mu k is greater than or equal to beta 1 summed up to beta k, since beta 1 through beta k aren't necessarily the largest k parts of mu. But we can rewrite beta 1 through beta k, the sum, using this formula. So beta 1 summed up to beta k equals lambda 1 minus 1 plus w1 plus lambda 2 minus 2 plus w2 up to lambda k minus k plus wk. Which equals lambda 1 summed up to lambda k minus 1, 2, 3, etc. summed up to k minus w1 plus w2 summed up to wk. Now w1 through wk aren't necessarily the k lowest letters from 1 to n, such as 1 through k are. So that means that, I'm sorry, this should be plus, because we've got plus signs instead of w. So this is greater than or equal to the sum of 1, 2, 3 up to k. Since that's greater than or equal to 0, then we've got mu1 through mu k summed being greater than or equal to lambda 1 through lambda k for all k. So that means that mu is greater than or equal to lambda in majorization. Also, observe that h lambda appears exactly once in this determinant of the matrix capital H lambda. Because we get the lambda 1 from the 1, 1 position. So we've got h lambda 1, h lambda 2, up to h lambda L. So we take anything else from the first row besides h lambda 1, the index is going to be greater than lambda 1. So we're not going to end up with the product of h lambda. So we have to pick this one. And then again in the second row, if we take anything, we can't take what's here. If we take anything to the right of this h lambda 2, then we're going to get a second component which is greater than lambda 2, and we're not going to end up getting the product lambda. So we have to take that, etc. So that means that the contribution of h lambda to this determinant is exactly 1. So to summarize, I guess that's the end of that proof. The summary is that S lambda, the Schur functions form a basis. for the Z module lambda n if and only if the complete homogeneous symmetric functions form a basis also. The end.